So good day sa lahat ng nakikinig ngayon. This is the formal start of our discussion sa structural theory. So syempre, everything starts with the introduction. Okay? So the last discussion natin is about the orientation. So ano lang naman 'yon, nagbibigay lang naman ako dun ng background regarding sa kung anong pagdadaanan nyo. So this time, ito na yung ating discussion proper, Introduction to Structural Analysis. So, i-play ko siya. Okay. So, Introduction to Structural Analysis. Again, I am Engineer John Ray Pacturanan. So, a faculty member of the Camarines Sur Polytechnic Colleges. So, yun. So, contents, ano ba yung ine-expect nyo na mga laman nitong nitong discussion natin? So, one is the historical background of structural analysis. Pangalawa is the role of structural analysis in structural engineering. Pangatlo is the classification of structure class. And pang-apat ay analytical models. So, by the way, ang i-discuss ko lang muna dito sa video ito. So, hindi lang ito isang video, puputulin ko to. So, for this recorded video, ang i-discuss ko lang is itong historical background. So, syempre, yung mga sumunod na videos, ito na yung role of structural analysis in structural engineering, classification of structure, and analytical models. So, historical background muna tayo, class, no? So, by the way, for early civilizations pala, ano ba yung historical background nila? So, according dito, since the dawn of history, structural engineering has been an essential part of human endeavor. However, it was not until about the middle of the 17th century that engineers began applying the knowledge of mechanics, so mathematics and science, in designing structures. Earlier engineering structures were designed now by trial and error and by using the rule of thumb based on past experience. The fact that some of the magnificent structures from earlier eras, such as the Egyptian pyramid, so it was built around 3000 BC. The Greek templates, it was built between somewhere 500 to 200 BC. Roman Colosseum and aqueducts 200 BC to 200 AD. And Gothic Cathedral from 1000 AD to 1500 AD still stands today is a testimonial to the ingenuity of their builders. So, syempre, ang structural theory class, bago pa lang naman tong subject or bago pa lang tong field of engineering. So, kumbaga, noong panahon na wala pang structural theory, according dito, no, so, kasi na-develop lang naman yon during the middle of the 17th century. So, before nun, nung wala pang advanced knowledge sa mathematics and science, trial and error lang ang ginagawa ng mga earlier civilization. So, parang halimbawa, ganitong design, ganitong shape, ay stable na dahil na-construct na ito sa isang lugar. So, ika-copy-paste na lang nila yon. So, actually, class, parang ganon or ngayon, ginagawa pa rin naman to yung trial and error natin. Pero, more on low-rise building lang naman siya. Halimbawa, kapag mga beam, normally 3 meters to 4 meters lang, no, kung ayaw mong mag-compute ng structural analysis sa mga sa mga bahay lang naman kasi hindi naman yan masyadong complicated. So, halimbawa, bungalow. So, kahit 3 meters lang o 4 meters yung distances ng kada beam. So, parang trial and error lang ang ginagawa ng design nun. Pero syempre, kapag mga high-rise structures, hindi pwede, no? Lalo na kapag mga skyscrapers. Hindi pwede na ang design mo is trial and error. Kailangan na natin dito, excuse me, ng advanced knowledge class ng structural analysis. So, sige. So, ngayon, structures of the earlier civilizations. Di kasi makita, no? Baba ko lang, no? Ayan. Structures of earlier civilization muna tayo. So, sige. So, yun, the Great Pyramid of Giza sa Egypto class, it was constructed during the Egyptian civilization as the resting place of the pharaoh, no? So, alam nyo naman na, libingan class. Okay? So next is the Parthenon. It is considered glass as the holy place in Greek civilization kasi kung hindi ako nagkakamali, ito yung mga parang meeting place ng Greek gods and goddesses according to their tradition. Okay, no? So ito um, yung iconic na design ng mga columns nila, ng mga pillars. For instance, I think, no, sa National Museum sa I mean sa Post Office sa Manila and the National Museum of the Philippines, yung tatlong buildings niya, may mga ganitong pillars. Sa Ateneo de Naga, plain lang na ganito, pero alam ko inspired yung apat na pillars ng Ateneo de Naga sa Greek. And ako, halimbawa, graduate ako ng Nabua National High School. So yun, may mga pillars din doon sa old or sa main building ng Nabua High. So, yung mga pillars na yun is inspired siya sa Greek architecture. So next is the Roman Colosseum. I assume most of you are familiar with this one. So this major events during the Great Roman Empire happens here. So kung ano yung purpose ng Colosseum ngayon, yun din yung purpose ng Colosseum noon. So ano siya? Wala naman doon nagko-concert syempre. Pero nandito yung mga battles, halimbawa, no? So, yung parang espadahan ng mga no, soldiers. So, dito. So, parang place for entertainment kung hindi ako nagkakamali. So, that is the Roman Colosseum. And lastly, the Notre Dame Cathedral. Unfortunately, alam natin na nasunog ito, di ba? I think last 2019, no? So, nasunog siya. So, yun. So, this is an example of Gothic structures that are mostly seen in Europe. So, yun class, yung ating Notre Dame Cathedral. So, next, no? After natin, nung earlier civilization, nagsimula yung trial and error method na matapos nung kay Galileo Galilei. So, ano ba yung contribution ni Galileo Galilei sa structural analysis, no? So, sabi dito, si Galileo Galilei from 1564 to 1642 is generally considered to be the originator of the theory of structure. So, siya daw yung parang, ano bang tamang term? Originator. So, parang sa kanya nang galing yung idea na dapat magkaroon ng theory of structures. Okay, no? Ulitin ko yun, no? Sabi, sa kanya nang galing yung idea na dapat may theory of structures. Okay? Kasi, bakit ko kailangan i-emphasize nun? Kasi babasahin ko na, in his book entitled Two New Sciences, which was published in 1638, Galileo analyzed the failure of some simple structures, including cantilever beams. Although Galileo's prediction of strength and beams were only approximate, his work laid the foundation for future developments in the theory of structures and ushered in a new era of structural engineering in which the analytical principle of mechanics and strength of materials would have a major influence on the design of structures. So, balik ako doon. Sa term natin, originator siya class. So, ibig sabihin, sa isip ni Galileo, parang gusto niyang sabihin na dapat merong theory of structures. Pero, in fact, si Galileo mismo, wala siyang na-contribute na any principle sa structural theory. Actually, dito lang natin mapag-uusapan si Galileo. So, parang sabi niya, uy, gawa tayo ng bagong field of science for structures. Parang, uy, gawa tayo ng theory of structures. So, parang siya yung nag-initiate ng idea pero wala siyang ambag. Yun yung literal na role ni Galileo dito sa history of structural theory. Siya yung nagsabi na dapat may theory of structures, pero siya mismo walang binigay na direktang ambag sa structural theory. So, ano lang siya, naglay lang siya ng foundation, nagbigay lang siya ng idea na dapat meron, paulit-ulit na ako, na merong structural theory. So, because of that idea, yung mga future scientists, nagkaroon na ng susundan. So, syempre, 'di ba lahat naman nagsisimula sa idea. Actually, yung ambag niya pala, sorry, may ambag naman siya. Yung ambag niya mismis yung idea. Okay, pero wala siyang theorem dito sa structural theory. Unlike kay Newton's, unlike kay Castellano, unlike kay Müller-Breslau. So, may mga ambag sila sa mga principles. Pero yung pinaka-layout, yung pinaka-idea galing kay Galileo, no? So, I hope, no, clear tayo doon. Next tayo. For the 17th and 18th century, so may mga scientist na tayo dito na pag-uusapan and tingnan natin kung ano yung mga contributions nila sa structural theory. So, una, si Robert Hooke. So, si Robert Hooke ang nag-develop ng law of linear relationship between the force and deformation of material. So, most likely, ang tawag natin doon is Hooke's law. So, si Robert Hooke ang nag-develop ng yun nga, sa pangalan niya, Hooke's law. Di ba nga, ang Hooke's law sa strength of materials, kung maalala nyo, stress is proportional to strain. So, yun yung idea ni Robert Hooke. Di ba? So, ano yun? Tapos, yung constant doon is the modulus of elasticity. So, next is the Isaac Newton formulated the law of motion and developed calculus. So, sa theory of structures kasi may calculus tayong mapagdadaanan. Pero yung mas importante is yung laws of motion. So, di ba class, alam niyo naman, simula pa lang sa statics, no? Simula nung nag-take ng statics, alam nyo, yung best na formula palagi, summation forces horizontal equals 0, summation forces vertical equals 0, summation moment equals 0. So that is the contribution of Newton, the laws of motion. In fact, yung sinabi ko is the Newton's third law of motion. Okay? So next is the Johann Bernoulli. Si Bernoulli naman, nag-develop siya ng principle of virtual work. So, yun. Ang work kasi gagamitin din natin yan sa deflection, no? As I said doon sa orientation natin, may ano tayo, energy method. So, sa chapter, ano ba siya? Chapter 9 yata or chapter 10 natin siya mapagdadaanan. Anyway, proceed tayo. Another, Leonard Euler. Si Euler, by the way, ang pronunciation nito is Euler. Dinevelop niya ang theory of buckling of columns. So, syempre, ang columns, di ba, nagbabuckle siya. Mahirap kasi siya i-discuss ngayon kasi dapat nasa strength of materials pa siya. Dapat alam niyo yung ibig sabihin ng word na buckling. So, most likely, mapagdadaanan niyo na lang siya pagdating niyo sa structural steel design. Basta ang dinevelop niya is the theory of buckling. And dito naman, si Charles Augustin de Coulomb, ang present niya the analysis of bending of elastic beams. Ang tawag natin doon is the elastic beam theory. Yung elastic beam theory, yung nag-lay down ng buong concept ng deflection and rotation ng lahat ng structures. Kasi hindi mo pwedeng i-assume ng structure is rigid. Lahat ng structure are deformable. Diba? So, yun, elastic theory dito. So, kapag may advance ka ng knowledge sa kasi sa analysis, there are two types of there are two types of design process. The elastic process and the plastic process, no? Pero wag na muna natin 'yung pag-usapan, nagsisimula pa lang naman tayo sa theory. So, next slide tayo. So, after ng 17th to 18th century class, this time sa 19th century naman tayo. So, dito, marami-rami ang pag-uusapan natin ng mga scientist. So, una, si mahirap, no? Pagpasensya nyo na yung magiging pronunciation ko kasi most likely mga French ito or German, no? So, halimbawa, si Claude Lois, ewan ko na dito, Marie Navier. So, pwedeng pakisearch na lang siya class sa internet kung ano yung pronunciation niya, no? Kasi hindi ko rin talaga alam kung paano siya babasahin. Subukan ko nga, no? Na i-search o subukan ko nga siya na hanapin kung paano siya basahin, no? Since may internet din naman tayo. Okay. Sige. Wala kasing wala. Wala man lang kung paano basahin, no? So, yun. Tingnan nga natin. Wala, di ko rin siya mahanap plus, no? Kung paano babasahin siya. And nevertheless, ayan niya. Basta si Navier, yun lang naman ang mga importante dito no apelyido. Okay, so si Navier. So this time, balik tayo no sa presentation. Ang ambag ni Navier ngayon class, so basahin ko lang. published a treatise on elastic behavior and structure in 1826, which is considered to be the first textbook in the modern theory of strength of materials. So, para madaling matandaan, ang ambag lang ni Navier is siya yung gumawa ng unang libro sa strength of materials. So, yun lang. Tapos, di ba? So, dito naman, si Bernard Paul, Emile yata yan, Clapeyron. So, yun, ang hirap ng mga French, no? Oo. Pagpasensyahan niyo na ulit ang pronunciation ko, but you may search the pronunciation kung paano. Basta si Clapeyron, o 'di ba? Clapeyron na lang. Si Clapeyron naman siyang nag-formulate ng three-moment equation for the analysis of continuous beam. So, i-discuss din natin ang three-moment equation class, no? Sa chapter 12 nyo. Kasama yan sa discussion natin. So, ngayon, pinag-uusapan muna natin kung sino-sino yung nakadiscover nun. Diba? So, next, si James Clerk Maxwell. So, presented the method of consistent deformation, which is sa chapter 11 yata natin mapag-uusapan, and the law of reciprocal deflection. So, yun. Yun yung ambag niya sa structural theory. Okay? So, next, si Otto Moore. So, si Otto Moore, napakaraming ambag nito sa class, sa structural theory din. So, he developed the conjugate beam method. So, kapartner ito ni area moment eh. And method of calculation of deflection and the Moore circle for stress and strain. Kung na-discuss to sa strength of materials, kung paano mag-drawing ng Moore circle, no? Pero kung hindi, okay din lang naman yon, madali din naman siyang i-self-study. So next, si Alberto Castellano formulated the theorem of least work. So ang tawag nga doon is the Castellanos theorem. Kasama siya ni virtual work method na magka-partner yan sa energy method class. Okay? So next tayo, another si Heinrich Müller-Breslau. Si Müller-Breslau presented the principle for constructing an influence line. Kung maalala nyo, mag-discussion tayo doon sa influence line, no? Sa sa orientation natin, which is chapter 7 siya. Influence line for statically determinate structures. So, si Müller-Breslau yung nagbigay ng way para mas mapadali yung pag-sketch natin ng mga influence line. Okay? And dito naman, si Charles Ezra Green, so he developed the moment area method. So, yun. Si moment area method, another way yan ng pag-compute ng deflection. Kasama yan ni conjugate beam method. So, di ba, nadidiscuss na natin yung double integration by history pa lang, no? Double integration method, tapos yung area moment, tapos conjugate beam, Castellanos, saka yung list work, yung virtual work method. So, lahat yan pagdadaanan natin class sa ating discussion dito sa structural theory. So, yun naman talaga ang pinaka-focus natin. More on mga deflection, rotation, and analysis of structures. So, tapos na tayo sa 19th century. This time class, pupunta na tayo sa latest, which is the 20th century. So, ano yung mga ambag sa 20th century? Dito, slope deflection method. So, si George Manny, pasensya na, wala akong nahanap na picture ni Professor Manny. He is, I think, an American, scientist or engineer. So, si Manny developed the slope deflection method, which is considered to be the precursor, no, of the matrix stiffness method. So, yun. Ang slope deflection method, kung maalala nyo, i-discuss din natin yan. Basta si Professor Manny yung nag-develop. So, ngayon, sabi nga dito, precursor of the stiffness or the matrix stiffness method. So, pag naisip nyo yung matrix, parehas tayo class ng naiisip. Ayan yung mga number of rows, number of columns na mga numbers. So, yes, bigyan kita ng hint agad sa structural analysis. Any structure can be transformed into its equivalent matrix form. So, sa advanced structural analysis, kapag may advanced na lesson na, more on nasa graduate school na rin kasi yun eh. Ang mga structure natin, class, nako-convert natin yan sa matrix form. Halimbawa, sa truss, na may matrix yan. Ang beams, mas lalo yan na may matrix yan. And ang frames as well, nagiging matrix yan. And because of that, na-program natin, na-develop yung computer, na-program din natin yung computation or yung the moment na na-matrix natin class ang structure, mas madali na siyang i-program sa computer. Kaya 'di ba may mga computer na tayo. So before na-develop ang matrix analysis, so kinonsider muna yung slope deflection method. Kaya lang, syempre, early 90s pa rin naman to class, early 90s. So early 20th century siya. So ibig sabihin wala pa nung computer development. Okay? So kumbaga, more on mano-mano pa siya. Kaya ang nangyari sa moment distribution method by Hardy-Cross, so basahin ko lang, moment distribution method, si Hardy-Cross, who developed the moment distribution method in 1924. So, the moment distribution method provided engineers with a simple iterative procedure. Pag sinabi nating iterative, paulit-ulit. Simple, ano lang siya, parang repeat step ganito until matapos ka. Kaya nga iteration ang ginagawa. Paulit-ulit siya hanggang matapos ka ng analysis. So, procedure for analyzing highly statically indeterminate structures. The method, which was most widely used by structural engineers during the period from 1930s to 1970s, contributed significantly to their understanding on the behavior of statically indeterminate frames. Many structures designed during that period, such as high-rise building, would not have been possible without the availability of the moment distribution method. So, ang ibig sabihin, yung moment distribution method, actually, ile-lesson ko rin siya as part of the discussion talaga. Ano lang siya, parang i-distribute mo tong moment from the word itself. More on basic arithmetic lang siya, tabular talaga yung computation niya dito. Wala siya masyadong complicated na mathematics, no? So, yun lang, mahaba. Simple nga, pero iterative. So, yun, paulit-ulit kasi yung process dyan. So, which is, madidiscuss naman natin yan, class. Huwag kayong mag-alala pagdating sa, pagdating natin sa moment distribution method mismo. Basta tandaan nyo, because of the moment distribution method, yung mga, yung mga structures, mga high-rise building, is naging possible na makonstruct. Kasi, mas accurate ng structural analysis. Noon, class, kung magtatayo ka ng isang high-rise structure, nangangailangan yan ng napakalaking foundation area. Tingnan nyo ang pyramid. Kaya yan naging pyramid kasi napakalaki nung base area niya. Halos ang mga simbahan noon napakalalaki ng kanilang base area. Kasi syempre, pag mas malaki yung base area, mas maraming portion ng lupa ang magdadala nung ating mas maraming portion ng lupa ang magdadala class nun bigat ng structure. Pero, because of the moment distribution, nakita nila yung process na pwede kang mag-construct ng matataas na structure using smaller land area. So, yun yung importansya. Kasi, habang nag-i-improve ang civilization natin, yung demand ng lupa ay tumataas. But of course, ang land is not, hindi siya masyadong rumarami. The area of land is, hindi siya masyadong nakakasabay sa pagdami ng demand. So, therefore, kailangan ng high-rise structures para at least maliit lang yung lupa, pero marami yung nag-o-occupy. And because of the moment distribution method, naging possible ang construction ng mga high-rise building. So, ganun siya. No? Ganun yung idea ng moment distribution. Pero, tandaan nyo, mostly mano-mano pa to kasi wala pa masyadong computer noon. But, sabi nga natin, balik ko lang dito. Dahil sa slope deflection method, na-formulate na class yung matrix analysis method. And during the mid-20th century, pumasok na ang computer applications. So therefore, unti-unti napalitan na yung moment distribution methods. So because of that, the availability of computers in the 1950s revolutionized structural analysis. Because the computers could solve large system of simultaneous equations, analysis that took days and sometimes weeks in the pre-computer era could now be performed in seconds. The development of the current computer-oriented methods of structural analysis can be attributed to, among others, so J.H.R. R.G. Rees, R.W. Clough, S. Kelsey, R.K. Livesley, A.T. Martin, M.T. Turner, E.L. Wilson, and O.Z. Zykewick. So, again, I apologize for some mispronunciation, no? Medyo mahirap din kasi sa akin, no, na mag-pronounce itong mga apelyido nila. But nevertheless, i-discuss ko na, syempre, sabi ko nga kapag matrix analysis, kaya na siya ng computer. Kasi, mas madaling naiintindihan ng computer class ang mga matrix. So, the moment na kaya mong ma-convert sa matrix ang structure, yun, pumasok na yung finite element analysis. Nandito na yung mga sikat na computer software like STAAD, ETABS, ANSYS, Abacus. So, kung hindi kayo familiar doon, mapagdadaanan nyo na lang yan pag nasa professional field nyo na or pag nagtatrabaho na kayo. So, yun. The computer application gives us a more accurate representation of the structure. So actually, hanggang ngayon, kaya nga wala na tayong 21st century sa slide kasi for this 21st century, improvement lang ng 20th century, improvement lang nitong computer application. So, to give you a summary, before ako mag-next slide, paano na-improve yung structural theory? So, for summary, earlier civilization, ang ginagawa lang nila is trial and error based on existing structure. Okay, no? So, yun yung una sa early civilizations. Pero, nung time ni Galilei, and the 17th and 18th century, nandito na yung pag-layout ng mga scientific principle for structural analysis, which I said, the Hooke's law, at the same time, the Newton's law of motion, and yung ating principle of least work. Okay? So, sa early civilization, trial and error. Dito sa Galileo Galilei era, dito na yung mga scientific foundation. Next, for the 19th century, sa 19th century naman class, ang na-develop dito is the classical methods of structural analysis. Ano yung classical methods na tinutukoy ko? The area moment method, the conjugate beam method, the Castellanos theorem, and so on. So, yun yung mga classical methods. And sa 20th century, na-develop na yung advanced method of structural analysis for high-rise structures and computer application. So, nandun na yung slope deflection method and the moment distribution method. So, ang pag-develop or ang pag-improve ng structural theory class is nakadepende sa kung paano nag-improve ang science and technology. So, di ba? Nung na-discover ni Newton ang classical mechanics, so, syempre sa physics to, yung classical mechanics, dun din na-develop yung, yun din na-develop yung structural theory. And habang nag-i-improve yung ating, computer o yung technology, halimbawa dito sa, 20th century, nag-improve yung computer, mas lalong nag-improve din ang ating structural theory. So, that is the brief history of the structural theory class. Diba? So, napakasimple lang naman nun. So, I hope na alala nyo yung mga tao na nag-develop, mga tao na nagbigay contribution, malay nyo, in the future, ikaw na rin ang magde-develop ng bagong theory sa structural analysis. So, i-end ko muna ang part 1 nitong video presentation na to regarding sa brief history of structural theory. So, thank you so much.